In the early 20th century, doctors noticed a terrifying shift in their wards. Lung cancer, a disease so rare a physician might only see it once in a career, was rapidly multiplying. Between 1900 and 1950, its frequency quadrupled, rapidly becoming the most common form of cancer among men. Around the same time, the consumption of machine-made cigarettes exploded. This graph shows cigarette consumption alongside the lung cancer death rate. You see a stunning parallel. The cancer curve replicates the smoking curve almost perfectly. But time series data is notoriously poor evidence for causality. Two parallel lines don't inherently prove one drives the other. Dozens of other factors fit the exact same timeline. We were paving thousands of miles of roads with tar, while cars began flooding the streets with leaded gasoline fumes and industrial exhaust. To a scientist in 1950, any of these environmental shifts were equally plausible culprits for the spike in lung damage.
A simple historical graph isn't enough to condemn a massive, ubiquitous industry. To separate a tragic coincidence from a true cause, researchers needed to find a way to isolate smoking from everything else. Proving cause and effect usually requires a randomized controlled trial. You take a group of people, flip a coin, and assign half a variable by pure chance, leaving the other half as a control group. But you can't run that experiment on smoking. Ethically and practically, you cannot imagine forcing randomly chosen people to smoke for 30 years to see if it ruins their health. Since scientists couldn't intervene, they were stuck with observational data, looking at people who chose to smoke on their own. This left their research vulnerable to confounders, lurking third variables that might be the true, hidden cause of the disease. Laboratory experiments on animals were starting to show results, but skeptics dismissed them as irrelevant to human biology. Without a way to mathematically settle the argument over causation, the tobacco industry could hide behind the ambiguity of observational data forever. In 1948, researchers Richard Dahl and Austin Bradford Hill attempted a new approach. They designed a retrospective case control study comparing hospitalized lung cancer patients to a healthy control group. The findings were shocking. Out of 649 lung cancer patients interviewed, 647 were smokers. Dahl and Hill calculated the odds against this being a coincidence at 1.5 million to 1. Yet, skeptics immediately pointed to valid loopholes. They argued the data was tainted by recall bias, the idea that sick patients might remember their smoking habits differently, and selection bias, because hospitalized patients aren't representative of the general public. Dahl and Hill escalated. They launched a massive prospective study, sending questionnaires to 60,000 British doctors to record their habits, then following them forward in time to see who actually developed cancer. The new data revealed a clear dose-response effect. Heavy smokers were dying from lung cancer 24 times more often than non-smokers. The more they smoked, the more the mortality rate climbed. Even with this overwhelming evidence, statistical purists refused to concede. It proved that data alone couldn't overcome a deeply entrenched scientific dogma. The opposition was led by R.A. Fisher, a giant of modern statistics. He introduced the ultimate defense for the tobacco industry, the constitutional hypothesis. This diagram illustrates Fisher's theory. He argued there might be a genetic trait, a smoking gene, making people crave nicotine and susceptible to cancer. For tobacco companies, this was a perfect trap. Because this gene couldn't be measured, the theory was nearly impossible to disprove. The stalemate held until Jerome Cornfield, a statistician at the National Institutes of Health, decided to challenge Fisher using the industry's own weapon, mathematics. Cornfield proposed a logical checkmate, now called Cornfield's inequality. If smokers have 9 times the cancer risk, a hidden gene must be 9 times more common in them. If 11% of non-smokers have it, 99% of smokers must carry it. It's biologically inconceivable for a gene to perfectly dictate buying cigarettes. Fisher's untestable theory collapsed into smoking ruins. Cornfield's logic proved that mathematical rigor could be just as decisive as a physical experiment, forcing the scientific community to finally acknowledge the reality of the evidence. This mathematical victory cleared the way for the landmark 1964 Surgeon General's report. It was the first time the U.S. government unequivocally stated that smoking causes lung cancer. Immediate public health changes followed. Congress mandated health warnings on every pack, and cigarette advertisements were eventually banned from television and radio. Cornfield's logic evolved into a technique called sensitivity analysis, a tool researchers still use to evaluate how much weight a hidden variable would actually need to overturn their results. This breakthrough freed scientists from the ideological requirement of a perfect experiment. It gave them a way to solve medical mysteries even when a randomized trial was impossible. The cigarette wars taught us that we don't have to be victims of uncertainty. By combining observation with mathematical logic, we can extract undeniable, life-saving truths from a messy and imperfect world.